There are planets out there that should not exist, not because they violate the laws of physics, but because they are too perfect, too precise, too specifically calibrated for life to be the result of random chance. Planets with exactly the right distance from their star, exactly the right size, exactly the right atmospheric composition, exactly the right axial tilt to produce stable seasons, exactly the right magnetic field to protect against radiation, exactly the right moon to stabilize their orbit. The probability of all of these factors aligning by accident, according to some calculations, is so small that finding even one such planet should be essentially impossible. We have found dozens, and some of them are more Earth-like than Earth itself was for most of its history. By the end of this video, you will understand why some of the worlds we have discovered in the last decade have made certain scientists quietly abandon the idea that we are alone, not publicly, not in press releases, but in private conversations and in the careful language of peer-reviewed papers that say, between the lines, that what we are finding does not add up. Let us start with what makes a planet suitable for life as we understand it. The habitable zone. You have probably heard this term. It is the region around a star where temperatures allow liquid water to exist on a planetary surface. Not too hot, not too cold. The Goldilocks zone. For decades, this was considered the primary criterion. A planet in the habitable zone of its star was considered a candidate for life. A planet outside it was dismissed. But we have learned that the habitable zone is just the beginning, just the first filter. There are dozens of other conditions that need to be met simultaneously for a planet to be truly habitable. The planet needs to be roughly the right size. Too small, and it cannot hold a substantial atmosphere. The right size. Too large, and it becomes a gas giant with no solid surface, or its gravity crushes complex biology before it can develop. The star it orbits needs to be the right type. Too large, and it burns too hot, and too briefly. Too small, and it produces dangerous flares of radiation that would strip away atmospheres and sterilize surfaces. The sweet spot is a star similar to our Sun or slightly smaller, stable enough to shine for billions of years without catastrophic variability. The planet needs a magnetic field strong enough to deflect the stellar wind and cosmic radiation that would otherwise strip its atmosphere and bombard its surface with lethal energy. It needs plate tectonics, or something equivalent, to cycle carbon and other elements through the crust and atmosphere, regulating the chemistry of the environment over geological timescales. It needs a large moon or some other stabilizing influence to keep its axial tilt relatively constant. Without a stable axial tilt, seasons become catastrophic. Ice ages last millions of years. The climate swings so violently that complex life cannot gain a foothold. It needs to be in a stable orbit, not too elliptical, not perturbed by the gravity of nearby giant planets into an unstable path that takes it alternately too close and too far from its star. It needs giant planets in the outer solar system to act as gravitational shields, deflecting incoming asteroids and comets away from the inner system where life is trying to develop. And it needs time. Billions of years of stable conditions for evolution to do its slow, patient work. The probability of all of these conditions being met simultaneously by random chance in any given planetary system was once estimated to be vanishingly small. So small that the astronomer Peter Ward and paleontologist Joe Kirschvink wrote an influential book arguing that complex life might be extraordinarily rare in the universe, that Earth might be close to unique, extraordinarily rare, that the conditions here were so improbable that they might have occurred only once or only a handful of times in the entire history of the observable universe. And then we built better telescopes. The Kepler Space Telescope launched in 2009 and spent 9 years staring at a small patch of sky containing about 150,000 stars. It looked for the tiny dimming of starlight that indicates a planet passing in front of its sun. What it found transformed our understanding of the universe. Planets are everywhere, not rare, not unusual, everywhere. Before Kepler, we knew of a few hundred planets orbiting other stars. After Kepler, we knew of thousands. And from those thousands, we could extrapolate to the entire galaxy and conclude that virtually every star has planets, that our galaxy alone contains hundreds of billions of planetary systems. But more importantly for our purposes, Kepler found Earth-sized planets, rocky worlds, planets in habitable zones, not just a few, dozens, and then hundreds, and the data suggested that rocky habitable zone planets might be among the most common types of planet in the galaxy. And then the James Webb Space Telescope arrived. JWST can do something Kepler could not. It can analyze the light that passes through a planet's atmosphere as it transits its star. It can detect the specific wavelengths absorbed and emitted by different molecules. It can, in principle, detect the presence of water vapor, carbon dioxide, methane, oxygen, ozone. It can look at a planet 40 light-years away and tell us what its atmosphere is made of. And what it has begun finding is extraordinary. Let me tell you about a system called TRAPPIST-1, a small, cool red dwarf star about 40 light-years from Earth. 40 light-years. In cosmic terms, this is next door. A signal traveling at the speed of light from that system would take only 40 years to reach us. TRAPPIST-1 has 7 planets. 7. All of them rocky, all of them roughly Earth-sized. 7. 3 of them sit squarely within the habitable zone of their star. 3 planets around a single nearby star with the right size and the right temperature for liquid water to potentially exist on their surfaces. When astronomers first confirmed the TRAPPIST-1 system, in 2017, it caused genuine excitement in the scientific community. Not the polite, measured excitement of a minor discovery. Real excitement. The kind that makes scientists forget their carefully cultivated reserve and say, out loud, that this changes everything. Because here is what is extraordinary about TRAPPIST-1. The planets are in what is called orbital resonance. Their orbital periods are related to each other by simple mathematical ratios. As the innermost planet completes 8 orbits, the second completes 5, the third completes 3, and so on in a precise mathematical chain. Orbital resonance can occur naturally. It is not impossible. Jupiter's moons, Io, Europa, and Ganymede, are in a similar resonance. But the TRAPPIST-1 resonance is unusually precise, unusually stable, the kind of configuration that, once established, can persist for billions of years without disruption. The kind of configuration that gives life the time it needs. James Webb has begun analyzing the atmospheres of the TRAPPIST-1 planets. The results so far are preliminary and contested. But there are hints, suggestions, atmospheric features that do not quite match what simple chemistry would predict. Nothing confirmed, nothing definitive, but hints. Now let me tell you about another world, one that has been in the news more recently and that has generated more controversy than almost any other exoplanet discovery. K218b, a planet about 120 light-years from Earth orbiting a red dwarf star. It is larger than Earth in a class of planets called subneptunes or Hycean worlds. Scientists believe it may be covered in a global ocean beneath a hydrogen-rich atmosphere. In 2023, the James Webb Space Telescope detected something in the atmosphere of K218b that caused immediate debate: dimethyl sulfide, DMS. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, by living organisms in the ocean. It is a biosignature, a chemical that, as far as we know, requires biology to produce in significant quantities. The detection was tentative, the signal was weak. The scientists who published it were careful and measured, saying it required confirmation and that alternative explanations could not be ruled out. But they also said something remarkable. They said that if the signal were confirmed, it would be consistent with biological activity in the oceans of K218b. Life on an ocean world 120 light-years away. The follow-up observations are ongoing. The debate continues. The scientific community is carefully, cautiously, waiting for more data. But the fact that this is a serious scientific conversation, that we are having peer-reviewed debates about possible biosignatures on specific named planets using data from real telescopes, is itself extraordinary. We are not talking about abstract possibilities anymore. We are looking at specific worlds and asking specific questions about specific chemicals and what they might mean. Now let us go further. Let me tell you about the planets that trouble scientists the most, not because they show signs of life, but because they show signs of something almost as strange. Super-Earths, planets larger than Earth but smaller than Neptune, between about 1 and 10 times Earth's mass. Rocky, potentially with atmospheres, potentially with oceans. Super-Earths are, statistically, the most common type of planet in our galaxy. More common than Earth-sized planets, more common than gas giants. And yet, our solar system has none. We have the rocky inner planets, Mercury, Venus, Earth, Mars. Then a gap, then the gas giants, Jupiter, Saturn, Uranus, Neptune. Nothing in between. Jupiter, Saturn. No super-Earths, no sub-Neptunes. The most common type of planet in the galaxy is completely absent from our own solar system. This is strange. This is so strange that planetary scientists have spent years trying to understand it. Why does our solar system look so different from the average planetary system in our galaxy? One answer involves Jupiter. The giant planet's gravity may have disrupted the formation of super-Earths in our solar system, clearing out the region where they would have formed and preventing them from accumulating. Jupiter acting as both a shield and a sculptor, shaping our solar system into its unusual configuration. If that is right, then our solar system is unusual, not typical. And Earth, which formed in this unusual system, may be more unusual than we thought. But here is the other side of that coin. Super-Earths, the most common planets in the galaxy, the ones we do not have, may be the best places for life to develop. Their larger mass means stronger gravity, which means denser atmospheres, more volcanic activity to cycle elements, more geological heat to drive chemistry. Their size means they can hold on to more water. Their prevalence means they are the most common potential habitats in the galaxy. If life tends to arise on super-Earths, then life may be extraordinarily common in the universe, far more common than any estimate based on Earth-like planets would suggest. We are looking for life on planets that look like Earth, but the universe mostly makes planets that do not look like Earth, and we do not yet know whether those planets are better or worse for life. We do not know. And that uncertainty, that gap in our understanding, is one of the most significant open questions in all of science. The planets are out there, hundreds of billions of them, many of them in the right place, many of them the right size, many of them with the right chemistry. And some of them, when we look at them carefully with our best instruments, show us things we cannot fully explain. Chemicals that should not be there, atmospheric features that do not match our models, hints that something is happening on these worlds that our current understanding of chemistry and geology cannot account for. We are at the beginning, the very beginning. We have been looking at exoplanet atmospheres for only a handful of years with instruments capable of detecting biosignatures. We have examined a tiny fraction of the candidates, and we are already finding things that make us pause. The universe is full of worlds, and some of those worlds, when we look closely enough, look back. Let us take a step back and think about what the accumulation of all this evidence means. In 1995, we confirmed the first planet orbiting another Sun-like star. One planet, a Jupiter-sized gas giant in a scorching close orbit around its star. Nothing like Earth, nothing hospitable. 30 years later, we have confirmed thousands of exoplanets. We have found rocky worlds in habitable zones. We have found planetary systems in resonance. We have found atmospheres with unexpected chemistry. We have found potential biosignatures on specific named worlds. 30 years, one human generation, and we have gone from one confirmed exoplanet to a universe teeming with worlds, some of them showing hints of something we dare not yet name. What will we find in the next 30 years? The extremely large telescope is currently under construction in Chile. When it is complete, it will be the largest optical telescope ever built, with a primary mirror 39 meters across. It will be capable of directly imaging Earth-sized exoplanets and analyzing their atmospheres with a precision that James Webb cannot match. The Nancy Grace Roman Space Telescope, scheduled for launch in the next few years, will survey the sky in infrared light and discover thousands more exoplanets. The LIFE mission, currently in development in Europe, is designed specifically to detect biosignatures on Earth-sized planets in habitable zones around nearby stars. We are building the tools to answer the question, deliberately, systematically, with instruments specifically designed to find life if it is there. And here is something that the scientists working on these missions say quietly among themselves when they are not being cautious for the cameras. They expect to find something, not hope, expect, based on the statistics, based on the prevalence of habitable worlds, based on the biosignature hints already detected, based on the chemistry of the universe and the abundance of the building blocks of life. They expect that when these new instruments come online and begin their systematic surveys, they will find something that cannot be explained by geology or chemistry alone, something that requires a different explanation. We have been asking whether we are alone for as long as we have been capable of asking questions. For all of human history, the answer was unknowable. The question was philosophy, not science. Now it is science. Now we have the tools to look. Now we are looking. The planets are out there. Perfect, improbable, precisely calibrated worlds orbiting distant suns. Worlds with oceans and atmospheres and chemistry that does not quite add up. And somewhere among the hundreds of billions of worlds in our galaxy, on one of those perfect, improbable, precisely calibrated planets, something may be doing exactly what we are doing. Looking up, wondering, building instruments to search the sky, finding hints of something they cannot explain. Next video, we go to the end of everything. We calculate exactly how the universe dies, step by step, era by era, until the last particle of light fades into eternal darkness. Subscribe to topvoidcast. If you are not afraid of the dark,